In the previous lecture, I wrote this x, listen. In the previous lecture, I wrote x long is equal to a dot, dot, dot. Of course, this is a dot. Please put a dot here. This is, I put dots over here and didn't put a dot over here. So the longitudinal states are these four, and then if you put a dot, you need to put dot everywhere else. I forgot this dot. Some student reminded me. Is that okay? So, all right. Another question was during the break was that what is this t halving time? Halving time, right? What is that? Well, halving time is simply, I mean, this picture doesn't look maybe too good. But if you had an oscillation that looks kind of like this, okay, and then you look at the signal looks really something like that, right? All right. So let's say you start from somewhere here, and this is time here, as time. This line is time. Okay. So if you would start from here, let's say this is some value x. How long does it take for the signal to become half? Okay, x divided by 2. So this time lapse that takes you from here to here, how long does this take? So this time here is halving time. Okay, how long does it take for this signal to half? Or if you would start here, okay, how long does it take to half it again? Here. If you would start from here, how long would it take to half it again? Basically, go back here. Okay? And in linear systems, they are kind of the same. So we say halving time is halving the signal. Understand? This is what a halving time is. And this gives us a measure of how long it takes for this to die out. I mean, in terms of linear systems, they only die out really, they only go back to zero going to infinity, right? If you look at the solution of the linear system, it looked kind of like this, right? E to the power lambda t. That's what we had in the linear system solution. So that lambda was the eigenvalue. So if the lambda is a negative number, as time goes to infinity, this would go to 0, and therefore it is stable or converging. However, as t goes to infinity, so since the airplane's flight will not be infinity, we will somehow have to have a measure of how fast it will die out. And one of the best ways to look at it is the halving time. And we say, you know, if the halving time is 2 seconds, we say, okay, in 2 seconds it's half. And then in another 2 seconds it will be half again. In 2 seconds it will be half again. So in approximately 6-7 seconds, nobody will see the signal anymore. It will be so small, right? But theoretically, it only goes to 0 when time goes to infinity. Of course, nature and the flight is never that perfect. But do you understand my point? That's what is halving time is kind of important. The period is important because I want to see how big the oscillation, I mean, how the oscillation behaves. You know, if you have an airplane, look up here real quick. If you have an airplane that oscillates like that, that's something. Or if it oscillates in a really long time, that's something else. Or if it oscillates like that, that's something else. So, oh, it has an oscillation is not the answer. I want to know how the oscillation really is. If it's really a long period for oscillation, let's say the period is 1 hour. Who cares about the oscillation? You go up a little bit, you go down, and nobody will feel it. But if the oscillation is about 3 seconds, the period, so which means every 3 seconds or 1 second, so you're kind of doing this, everyone will get sick in the airplane, right? Or if the oscillation is, say, 0.1 seconds, the period, which means it is how many hertz? 0.1 second oscillation period is 0.1 second. How many hertz is that? 10 hertz, right? If you have a 10, which means 10 cycles in 1 second. So you're going like this. That's also an oscillation. And people will not get sick, but people will be very uncomfortable because they will constantly have that vibration in their bodies. All right? So as a result, the period or the frequency of the oscillation is also very important. We need to know about this because it will determine our comfort. So how do we calculate the period in something like this? Again, this is something you should have seen in system dynamics. If not, go back to your books. Periods of a system like this, you can calculate it in the following way. It is simply 2 pi divided by omega. Okay? The halving time will be calculated by 0.693 divided by the real part. Okay, the real part of the eigenvalue. And how many cycles does it take to halve? That's quite straightforward, right? It is how many what's the time divided by the period. So this is how we will calculate this. Now for the period, it will simply be this. For example, let's calculate for this one. Lambda, let me put this a little up here. Okay. So let's look at the period for the first one. For the first one, it will be 2 pi divided by omega, omega meaning the imaginary part of the eigenvalue, okay? Imaginary part of the eigenvalue. So in this case, for the first one, it will be 0.8875. So can someone calculate this real quick? 2 pi divided by 0.88. Do you have a way to calculate it? What is it? 7? 7 point? 9? 9. Okay. So that's good enough. I mean, come on, it's 7 seconds. Okay? So let me put 7.0. I trust you, okay? I don't know the number. Is that okay? Want me to calculate it again? That's right. Good. We have 2 people who say it's right. Seconds. So the period is 7 seconds, approximately. Okay? 7 seconds. So in 7 seconds, one period of the oscillation is finished. Good. Let's look at the halving time. The halving time is, for the first one, is 0.693 divided by the real part, which is 0.37, and that is equal to, can you calculate that again? Should I do it over here? Should I do it over here? What is it? 1.87 seconds. So it is 1.87 seconds. So it's approximately almost 2 seconds, right? It's approximately 2 seconds. Less than 2 seconds, 1.87 seconds is the halving time. So in 1.87 seconds, the signal is halved. So in 2 seconds later, it's halved again. 2 seconds later, halved again. Probably in 6-7 seconds, you don't see anything anymore. Yes?
John, why don't we include the effect of the short and 4?
Of the eigenvalues of 3 and 4? Well, it's going to be calculated here. We will do that too. So I'm only looking at the first mode. Okay? So you wonder what the behavior of the airplane is in total. It is this plus this. Remember when we did the eigenvalues, we had the particular solution and then we had the general solution. The general solution was a linear combination of the 2 particular solutions. So this is one particular solution, this is another particular solution. You add them together, that's the solution of the airplane. So the airplane will do this plus this. It will not only be this. Okay, that's an important point. Because the matrix looks like that. It's a 4 by 4. Okay? So you have 4 eigenvalues, 2 complex conjugates. And if you recall again, in your second in the second week, I think I did that. Each of these eigenvalues, you add them up together, and that is the total solution of the behavior. Will be one plus the other. So we are looking at only one, and I'm going to look at the second one, and if you add them together, that's the total behavior of the airplane. Does that make sense? Okay. So the third thing I'm looking at is how many cycles does it take to halve the signal, right? How many cycles do I take to halve the signal, and how many cycles do I take? 1 divided by 8.6 divided by 7.07. What do I get here? 2.6. Okay, 0.26. So in cycles. So in approximately a quarter of a cycle, in a quarter of a cycle, it already dies out, right? Dies out. Let's do the same thing for the second line, for lambda 3, 4. Okay, period again. This is for lambda 1 and 2. And we're going to do the same thing for lambda 3 and 4. Period is 2 pi divided by, now it is 0.072. Again, can you tell this to me? It should be 93.54 seconds. Halving time, do again the same thing. 0.693, you should find something like 210 seconds. And the cycling, how many cycles does it take? 2.25 cycles. What is it? So this one here is the first eigenvalue, 1 and 2, and these are for the eigenvalues 3 and 4. Yes?
Where does this 693 came from?
Yeah, it's in the system dynamics book. It's a nice approximation for halving time. Okay? For linear systems. Really, it's in the system dynamics book. I mean, the derivation of that number it's an approximation. It's a good approximation. It's in the system dynamics book. Okay, so go back to that chapter. Halving time is important. Okay? How else do you find halving time? How do you find a halving time for a linear system? Do you remember? I mean, I don't know. What did you learn? Anyway, this is one way of doing it, okay? So, I mean, those things are useful, finding halving times, doubling times. If it was diverging, we would like to know what the doubling time is. How does it double? The signal doubles. How fast does it increase? What is the period? What is the frequency? And all this of signals. Yes, please.
Is it normal to find a half point in one cycle?
Well, that's the calculation. I don't know if it's normal.
We will find 0 point in one cycle also.
Yeah.
And maybe we can find bigger numbers in other cycles.
Let me just first explain it. If you still have that question, then we'll go back, okay? Because I haven't finished explaining this. So let's look at the modes, okay? This is what we found now. Let's try to understand. This is all longitudinal dynamics. Listen, this is important. This is longitudinal dynamics. So the behavior of the aircraft in this direction, okay? This is the lateral. So this is the longitudinal. So what do we have? We have 2 modes. We have one oscillation where the period is 7 seconds. So you go like 1, 2, 3, 1, 2, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. So you have one sort of an oscillation. The second one has a period of 93 seconds, which is very long, 1.5 minutes. So you go 1.5 minutes, you go down, and then you go down, and then you go up, right? It's 93 seconds, very long. This one here, it halves in less than 2 seconds. So it's a short period. It's a much shorter period, right? The oscillation is a shorter period, but it halves in 2 seconds. So which means you have this 7-second behavior, but it halves in less than 2 seconds. And then in another 2 seconds, it's halves again. In another 2 seconds, it's gone. So basically, you can safely say in about 5-6 seconds, you don't see it anymore if the disturbance is not too big. Okay? So it takes about a quarter of a cycle. What is a quarter of a cycle? Can you imagine a quarter of a cycle? If this is an oscillation, a quarter of a cycle is just here, right? If you divide 1, 2, 3, 4, right? Let's say these are 4 cycles. A quarter of a cycle is about here. So it already halves while it's doing that. So that's what it means. So it's not even a full cycle before it halves. So how many cycles does it take? I mean, it halves in 1.8 seconds, and the period is 7 seconds. So before you're even doing a quarter of the cycle, the signal has already dropped, right? So I'm not even sure if you can see the whole cycle, because that means before you finish this, right, you already have you already half the signal 4 times. I mean, halving of the halving, so you actually halve it a lot more, right? So it's gone very quickly. If you look at this one here, the halving time is 210 seconds, which is quite large, right? It is more than 3 minutes, 3.5 minutes. So which means it takes 2 cycles, 2 periods, until you actually halve the signal. Okay? So this is something that takes a really long time. The period is long. It will die out not that fast. It will be around for a long time if you leave the airplane by itself. But fortunately, it is quite slow, so the passengers won't get sick, right? If you leave it too long, they will get sick, but it's not like they will feel it a lot. But here, this one they will feel. Fortunately, it will be gone very quickly. Okay? Very typical for all airplanes. Very typical, and therefore they have names. The first one is appropriately called the short period mode. Because the mode is the oscillation is much shorter, right? The period is much shorter. And the second one is called the Phugoid mode. Okay, it's called the Phugoid mode. Phugoid. That's the Phugoid mode. 2 modes in the longitudinal dynamics for most airplanes. Is that okay?
And which one is important?
Both of them are important. What is the behavior? What is the behavior of the airplane now? Is it this one or is it this one? No, it is the combination of both. Both. That's what we call the modes. For example, if you have an oscillation, if you have a vibration on a beam, right? We call the first mode the second mode of vibration, the third mode. You have the rigid mode of the beam, and then you have this one, and then you have the second one and the third one, right? All these modes. What is the real behavior of the beam? It is a combination of all of them. So here, what does the airplane do? It does this plus that. But each of them can be separated in terms of 2 modes. So if you have an airplane, so what does this mean? Let's think about that. If you have an airplane that is in steady level flight, okay, so you give a disturbance in longitudinal dynamics, what's going to happen? Now you're here, you want to go back to the equilibrium point. How do you go back? You go back by doing both of them at the same time. First, the first one will start, it will die out it will start doing that, die out very quickly. At the meantime, the long period will be there too. So you would be doing that, it will be dying out, but the phugoid will continue. So which one is more important? Well, that's a question of what is important to you. I mean, is the first oscillation important to you, and the phugoid is a long oscillation? Or you don't care about the first one, but you care about the long one? Okay? So at the end, as aerospace engineers, you need to know both. Because sometimes the short period might be important, sometimes the phugoid might be important. Understood? So when I say it's a combination of both oscillations, think of that. For example, let's say you have something like this, and then on top you have a much shorter oscillation. So what is the total combination? A total combination is a combination of these two signals. So if you add them together, you might see something like that. I don't know. You know, this plus this might equal this. So this is your behavior. It's this plus the signal. And this is one mode, mode number one. We call this a mode, and this one we call another mode. Let's call this mode 1 and this one mode 2. And the real behavior is mode 1 plus mode 2 of the aircraft. Is the concept fine? Do you understand the concept at least? Okay. There's one more thing I would like to tell you about this. And it's this part. You have that? I mean, it's kind of a simple picture. Let's look at this one more time. What is this? Sorry. This was the longitudinal dynamics. And we looked at the eigenvalues of the longitudinal dynamics. And we keep talking about oscillations. Right? And look up here. I keep showing you, saying that the airplane will, look up here, the airplane oscillates like that. Right? Well, I don't really know that because I have 4 states here: velocity, angle of attack, angular rate, and theta. Now, when I say oscillating, which of these variables is really oscillating? Is it all 4 of them? Or does one oscillate more than the other? Right? Because I keep showing you that picture, the longitudinal oscillation, but how about this one? Maybe the velocity is only oscillating. Maybe the airplane is doing this. Slowing down, going faster, slowing down, going faster, slowing down. That's also an oscillation, right? If you plot u versus time, velocity versus time, you will go faster, slower, faster, slower. That would be also an oscillation. So it doesn't have to be like that. It can be faster, slower, faster, slower. Or, for example, angle of attack. It could be doing this, 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 this. That's also an oscillation. Well, if you do this, you probably slow down as well. But in order to do this, you need Q. Otherwise, you can't do it. Right? You need the angular rate. And if you do this, you probably also generate a theta. So you do this, everything is oscillating together. But who is doing more? Is it more a change in angle of attack? Is it more a change in velocity? Is it more a change in theta? That we didn't answer in this question yet. It seems to be a combination of all of them, but one might be more dominant than the other one out of these 4. Okay? So that picture that I'm painting you, saying that this is the oscillation, might not be exactly true. Okay? So how do we know which of these variables will oscillate more? Is there a way you can think of? We do what?
We will check the A matrix. We compare the numbers.
We can look at the numbers, but they are all interconnected. It will be hard. There's a much easier way I haven't showed you yet. we look at the eigenvector. The eigenvector is helping us to tell in which direction we have more movement, let's say. Okay? And we will do that after I do the lateral. We will look at the eigenvector and tell which one is oscillating a bit more. Is that fine? Okay. So this is as much as I want to tell you about this one. Okay? But please remember these names and never forget them as long as you are an aerospace engineer. A fixed-wing airplane in longitudinal dynamics has two modes, short period and Phugoid mode. Okay? Good. So what I'm going to do next is we are going to do the same thing for the lateral dynamics for the same airplane so that we find out what the modes are in lateral dynamics. Again, this is very typical and very classic for fixed-wing airplane. For the same Boeing 747 flying at 40,000 feet Mach number 0.8 Mach for lateral dynamics. So A lat will, the lateral dynamics of the A matrix will look like this. Six 1.1458. And therefore x lat, of course, is V, P, R, and phi. Okay, the A matrix in lateral dynamics for the same Boeing 747 airplane. We are again going to look at the eigenvalues of this. Well, it doesn't matter, but this matrix is written in this order. Okay, that's why I'm writing this all the time, because people can write it in different orders. Doesn't matter, but this matrix is written in this order. Okay. All right, so let's look at the eigenvalues of this. All right, that's the whole idea here. Going to look at the eigenvalues. Hopefully this will work. Okay, so this is the 747, by the way. Okay, we are looking at this airplane. Just in case you don't know what the Boeing 747 looks like, this is what we are looking at. All right? All right, so here is my here's my MATLAB again. And what do we need? We need the lateral dynamics, right? I should have written it somewhere here, so it should be somewhere. Okay. This seems to be the, is it? Good. Is that correct? You're sure? A lat is equal to answer, so that's it. Looks like our matrix, right? Okay. Lateral dynamics, eigenvalue of the A matrix. Ready? You're going to see something you'll never forget. So here it is. Ah, there you go. Okay. Don't forget this one. So, again, very typical. Lateral dynamics of a fixed wing airplane. Okay? What do we have now? Everything stable? Good. What do you see? Oscillations? One oscillation, complex conjugate. Two are going back to zero without oscillations. Which one is the fastest? 0.5. That 0.5 will die out very fast, whatever it is. The slowest is this one here. Look at this, 0.007. It is really close to the imaginary part, imaginary axis. So, you know, there's a very good chance it might just cross over to the dark side very quickly, right? Because it's so close to the imaginary axis, right? But it is still stable, but it will take a long time for it to correct, right? This one here. And this one will die out very quickly. This one is kind of in the middle, but it has an oscillation. Okay? Again, very typical for fixed-wing airplanes. So please write those numbers so that we can look at do the same analysis. Lambda 1 and 2 is minus 0.033 plus minus 0.9465. Lambda 3 is equal to 0.562. And lambda 4 is equal to minus 0.0073. So, these are the eigenvalues that we found. So, let's look at, again, at the complex plane. So, we basically have, again, 4 eigenvalues. One of them is really close, so it's here. Okay. To the imaginary axis. One of them is really far away. It's actually really, really far away. This is not even scale, right? Minus 0.5. This is really close. Minus 0.007, if you recall. And here you have something over here that would be 0.003. Oh no, 0.03. With oscillation. So you have basically those 4 eigenvalues with one oscillation in between. So this is one oscillation. And these two here, they are they're eigenvalues without oscillations. Okay, so let's put this into, again, do our table for this. Now we can go a little faster because we know how to do it. Lambda 1 and 2 is over here. Okay, periods. Halving time. Number of cycles, or how many cycles does it take to halve? And then we'll have the name. And then we're going to do it for the third one. And we're going to do it for the fourth one. Okay. So the third and the fourth, let's start with the first one, right? Halving time. So how do we find the halving time? Remember how we find the halving time? The period, I'm sorry. How do we find the period? Period for the first one is 2 pi divided by 0.94. Can you tell me what this is? Should be something like 6.65. Do you have that? So the period is 6.65. It is similar to the short period mode on the other side, right? That was 7 seconds. Now this is 6 seconds. But this is now in the lateral dynamics. So the lateral is here. Look up here. This is the lateral dynamics of the airplane, right? This is the longitudinal dynamics. And this is now the lateral dynamics. So you have some sort of an oscillation in the lateral dynamics with a period of 6.65. How about halving time? The halving would be 0.693 divided by 0.033, and you should find something like 21 seconds. So 21 seconds is halving time. So not bad. How many cycles will it take to halve? That's 0.16. So it takes approximately 3 cycles to halve the signal. And in another 3 cycles to halve it again. Another 3 cycles to halve it again. So you're halving. So that means, after probably like 10, 12 oscillations, it's probably very small at that time. Okay? How about the period for lambda 3? None, of course. There's no period for lambda 3. Lambda 3 doesn't have a period. It is a signal that kind of looks like this. It doesn't oscillate. It immediately goes back to 0, right? Looks like this. If this is your signal x, x would go to 0 like that. There's no oscillation because there's no imaginary part. Same thing for lambda 4. Okay? But you can calculate halving time again. It's the same calculation. You take the halving time is 0.69. Let me do it here. 0.693 divided by, let's do it for the third one, 0.56. What do you get? You get 1.23 seconds. 1.23 seconds. Okay? So it's a really fast one because it dies out quite fast, right? In 1 second it's half. Another second it's another half. So in 5 seconds you halved it, so nothing is left. How many periods does it take? No periods, right? No cycles, so that's gone. Let's do the same thing for lambda 4. So that's not going to be pretty, I can tell right now. T1.5 is equal to 0.63 divided by 93 divided by 0.0073. So that's going to be a small number, right? That's 95 seconds. So it takes quite a long time to halve this guy. 95 seconds, 1.5 seconds, or 1.5 minutes. That's only halving, so you wait another 1.5 minutes. It's kind of like the Phugoid mode, remember? The Phugoid mode was actually much worse. It was 210 seconds to halve, right? Okay, good. Now we have oscillations here and something like that over here. This one is an oscillation in the lateral dynamics, right? Period is about 6 seconds. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's the oscillation. And then the halving time is 21 seconds, so it takes about 3 oscillations until it halves, and then another 3 oscillations until it halves, and then 3 oscillations until it halves again. This one here dies out very quickly in 1 second, right? Whatever it is, it goes back very quickly. And this 95 is also, it's quite long, and it's close to the imaginary part. Now, as I said, these have names. And again, names that should never be forgotten, since they are very similar in every fixed-wing airplane. This one is called the Dutch roll mode. The Dutch roll mode is an oscillation. We'll talk about this a little later, as I said, when we look at the eigenvectors. But the Dutch roll mode is really a motion of the airplane that kind of has everything in it, and it looks like a skier. You know, someone who skis like that. The motion looks kind of like a skier. So the motion of the airplane, the Dutch roll mode, is something like that. Okay? So it has a little bit of a roll. It has a little bit of a side slip. Okay? It has a little bit of changing, of course it has a p, the angular rate. Okay? So the airplane is kind of doing that. That's the Dutch roll mode. And that is that oscillation that you see over there. So it is kind of like a ship, you know, when you have a ship and the ship does kind of like this when it has a wave or something. You have seen that probably, right? A little boat or something. If you have a little wave, the boat starts doing that. Right? This is a similar, but it has quite a bit of a yaw change as well. So it is kind of doing that. It's more like a skier type of movement. Okay? You might think of a Dutch skier. And that you can remember, it's a Dutch roll mode. Okay? That's one. This one here, this one is called the roll mode. As the name suggests, it is predominantly in the roll axis. Okay? It's this one here. So if you have an airplane, you give a disturbance, the airplane will start coming back. So that's that mode. So you give this, it will come back. Okay, you give that, it will come back. That's the roll. That's a roll mode. And it is quite fast. In 1 second it halves. So airplanes are quite stable in the roll direction. So you give this, it will come back. You give that, it will come back. Okay? So that's that. So you have this plus this. That's the roll mode. So what is the behavior of the airplane? It's all of them. You add them together. Right? So you give a gust, the airplane will do this, and then start doing the Dutch roll. All right? So, and the third one, that is mostly in the yaw direction, and we call it the spiral mode. That is mostly in the yaw direction. Okay? Spiral mode. I will bring my airplane and during the break I show you it a bit better. The spiral mode is mostly in the yaw direction. So you give a disturbance to the airplane, it will start doing that. Okay? Rotating. This is the spiral. And it will start doing that, you will go. And it will take 95 seconds to half and then a really long time, minutes and minutes, to get out of the spiral mode, which means you do this, and if you don't touch it, eventually it will just level out, but it will take quite a long time. So if you don't touch the aircraft will spiral, turn, spiral, and at some point it will just get out. That's what this means, it's stable. Now for many airplanes, this mode can actually be unstable. It can be unstable because if you look at this, if you look at here, here. If you look at this, I told you this number is very close to the imaginary part. But for many airplanes, it can actually move over to this side, to the unstable side, very quickly. Not quickly, but if you design your airplane in a certain way, this mode can actually appear over here. From a practical point of view, it is not any different from this or that. Instability is not that horrible if it's controlled well. What I'm trying to say is that, let's say you have an airplane that spirals, and then gets out. But you have spiraled so much You don't really want, and that's because of a little gust, right? I mean, you're going like this, it's a little gust, and you start spiraling. Not good, right? So what do you do if you start spiraling? Well, the pilot's, it's there. He will just take the airplane and move it back. It's like your car. Your car does sort of like a spiral too, right? If you don't touch the controls, if there's a little bump on the road, your car might actually start going that way. What do? Oh, my car is unstable, I'm dead. No, you take the wheel and go back, right? So it's the same thing over here. The pilot will just take the airplane and move it back here. So at that point, it really doesn't matter if the spiral mode is stable or unstable. Stable means this: you don't touch it at all. Okay? You give a disturbance, and you see if the airplane is coming back or not without touching the controls. Okay? That's what the definition of stability. Remember the pendulum, right? We took it up here, we left it, and it was moving, and it was coming back to the equilibrium point. Nobody was touching it. So that's what we call a stable equilibrium point. If somebody would touch it, it might never come back to the equilibrium point, but that's not the point. The point is, if you don't touch it, will it come back? And if the pendulum was upside down and it was unstable, you left it, it would fall, right? Well, but I can balance it maybe from the bottom, right, and make it stay there. But the point of stability, or the definition of stability, is if you don't touch it, will it come back to the equilibrium point? And that's the same thing over here. If you don't touch it, the spiral mode seems to be stable, but it's a really long mode, right? It spirals, and then eventually it will come back. Okay? But that doesn't mean that the pilot will not touch the controls. It's like your car. All right? So what is the behavior of the airplane? The behavior is all three of them, right? So what's going to happen? Look up here. What's going to happen to the airplane? You give a disturbance, okay? It will first roll, the rolling. Let me say I hit the airplane from the side. So it will roll. The roll will die out quite quickly. The Dutch roll will persist, right? The Dutch roll will start. But at the same time, you will start spiraling. Okay? You spiral. And at the same time, what happens is that the Dutch roll will die out. And the spiral will continue. And eventually, the spiral will die out as well, and we are back on track. Stable airplane? Yes. But you went through all this until you actually come back to the equilibrium point. So sometimes, I told you, stability, the way we are talking about it, is we talk usually about static stability. That's what this is. The static stability looks at, is it stable or is it unstable? Right? What is the tendency? Is the tendency to go back to the equilibrium point? Right? In this case, yes, it is there to come back. So we call this a static stability. The answer of static stability is the equilibrium point stable or unstable? We say, yes, it is stable, no, it is unstable. We really talk about static stability. So the answer for that is yes or no. It is stable or unstable. It's a stable mode, unstable mode. But sometimes the stability, the static stability part is only half of the story. The other half is what we call dynamic stability. And this is all that. In other words, what happens as you go back to your equilibrium point? Is there an oscillation? How much time does it take? What is the halving time? You know, those kind of questions we are asking for dynamic stability. So oftentimes, the static stability, as I said, is only half of the story, but sometimes the dynamic stability is even more important. For example, if I have an unstable mode, like the spiral mode, yes, it is unstable, but it takes such a long time, or it is easy to correct, or it takes 95 seconds to halve, or it could be an unstable mode, and it would take 95 seconds to double. So we have enough time for the pilot to correct, right? Or, I mean, you see, all these three modes are stable modes, but they are very different in nature, you see. I mean, it's not enough to say we have three modes that are stable. Oh, we are done. Our work is done as aerospace engineers. It's not done. We have three stable modes, but they're very different in nature. One of them is probably you don't even need to deal with this because it dies out so fast. This one is so slow that the pilot probably has to do something, or we can do it in a controller, but it is certainly very different from an oscillation that has a period of 6 seconds. Okay? So please understand that. I think we made that definition at the beginning of the class or in the first weeks of the class. We have two things, right? We have static stability and we have dynamic stability. So static stability is the initial tendency of a system after it is perturbed from its equilibrium point. Is the initial tendency, please add here, to turn or not return to its equilibrium point. Static stability is the initial tendency to return or not return to its equilibrium point of a system after it is perturbed from its equilibrium point. An aircraft is statically stable if it has an initial tendency to return to its equilibrium point. After an angular displacement or change in translational velocity. If tendency is to diverge, we call it statically unstable. And in all cases, no pilot inputs. With no pilot inputs, and equilibrium point in this case, we mean the trim point. Okay? And this is the definition of static stability. Or statically unstable, or we call it statically stable. And we can say a similar thing for dynamic stability now. Stability deals with the dynamic characteristic the ones that are related with time of the system after a perturbation from the trim point or equilibrium point, of course, right? Dynamic stability deals with the dynamic characteristics, basically characteristics related to time of the system after a perturbation from the trim point. Okay, and this is dynamic stability. So let's give again a short break. Be back here by 11:50.